Hello and welcome to episode 2 of C++ Weekly. I'm your host Jason Turner. Once a week we'll pick some topic of interest in C++ and dig into it with some live coding. In this episode, we are going to look at the cost of using statics. Now if you listened to the previous episode, you might have noticed that I commented on the side that there's some cost with using statics, and I didn't really dig into that. And it's entirely possible that that surprised some of our listeners. So I'm going to dig into that now and show you what I mean by the cost of using statics. And also, for this episode, I am using a different color scheme on my terminal. So if anyone has any feedback as to what is more readable, please let me know. So to start with, we are going to look at this example code that I've created using the Interactive Compiler Explorer, gcc.godbolt.org. If you have never used this tool before, I strongly recommend looking at it. It is a great way to explore what the compiler does in certain situations. So we have created a simple struct. It is called C. And in this struct, we have a static that is being created using the construct-on-first-use idiom. So this static doesn't really exist, the string s. Well, that's a poor way to put it. The string s has not been constructed until the first time that this magic static function is called. Now, if you're not aware, there was an enhancement to C++11 guaranteeing that the initialization of static variables happens in a thread-safe fashion. GCC had always implemented the initialization of statics that way, but Visual Studio was a little behind the curve on it, and it is not until Visual Studio 2015 that we actually have proper static initialization support implemented. So in this code, we have our magic static function that returns a const ref to the string s that is assigned the value of Bob, and the value is returned here on line 11. And then we have a local reference copy, if you will. It is a reference, not a copy of the string, that is constructed using class initialization on line 13. So when the object of type C is constructed, the member variable s is assigned a const reference of the value that is returned by the magic static function call. And then we also have this function called magic static ref that we are using to get a reference back to the member variable s. Notice that magic static ref on line 15 here is not declared static. So it is returning back a reference to the member variable s as opposed to a reference to the static variable here declared on line 10. It's also important to note, in both cases, all these values are every version of this, the member variable s and the magic static ref function and the magic static function itself, they are all returning pointers to the same value, to the same object that is contained here on line 10. So what we're trying to do is determine how much overhead there is in accessing a static variable. If you stop and think about it, the fact that a static variable is guaranteed to be constructed in a thread-safe manner requires that the compiler must have some way of determining if the variable has already been constructed, and if not, performing a lock and constructing the variable for us. So we have our example here of simply calling the function magicStatic.size 3 times and then returning it. I want to illustrate what the compiler has to do. So we can see line 24 in our source code is highlighted blue. We'll scroll to where this highlight is, and we can see that the compiler has to make a call to this function, magicStatic, for each call to the size function. And this seems pretty reasonable. But if we jump to this function where it is being called, so that is label 11. Let's get ourselves oriented here. So here's the magicStatic function that has to first check to see if the value has been initialized. If not, then it needs to jump to the initialization routine, which is L11. If it has been initialized, then it will simply return a reference to the contained value. But this compare, to check to see if the guard variable has been set, must be executed every single time. So we end up with 4 distinct function calls that must have a thread-safe comparison to see if the value has been initialized or not. So flipping things around a little bit, I'm going to comment out this block of code and uncomment this other. That does essentially the exact same thing, but instead of calling the magicStatic function each time, it is going to reference our magicStatic ref function, which, as we saw earlier, all it does is simply return a reference to, if you will, a cached reference to this variable s that was created for us in our static function. And now we can see we still have colorize turned on, but the compiler has completely eliminated all of these calls to magicStatic ref.size because it knows that there are no side effects with those calls. So we do not have to pay the expense of accessing this variable that is created in our static function. We can see the compiler has 29 instructions that it is executing. And just for educational purposes, we can double the number of calls and nothing changes at all in the output. So what I would like to do for the rest of this episode is try to quantify the amount of overhead that there is in using statics without maintaining our own reference to the variable after we know that it has been initialized. So, we have our 2 examples, just as we were looking at in the GCC Compiler Explorer. Make sure they're equal. Now, what we want to do, again, is try to quantify the difference here. But part of the problem is that, as we already saw, the compiler was able to completely optimize away the call to the static ref.size. So we're going to try to see if we can convince the compiler to not optimize that away. If we do, I don't know, some I less than very large number. Now, there is a very good talk that was one of the main sessions from CPPCon 2015 about code optimization by Chandler Carruth, and I do recommend that you go look at it because it has some very good examples on how to run micro benchmarks, that is, and we would be smart to use that here, but we aren't at the moment. So we shall not get the overhead of constructing our object each time. And we shall try to just sum up all of these values and then return total size so the compiler doesn't think we are throwing it away, which will probably give us a warning because we are returning a size t as an integer, but we're not going to worry about that for the moment. So that looks about right. We're going to total this up. Let's see, 10 million times. Is that right? No, that's 100 million times. All right. Oh, always forget to add the standard. And I want to turn on optimizations. So that returns basically instantaneously. But one thing I like to do is to use callGrind tool to actually count the number of instructions that have been executed. So we see in this case, we have 1,875,000 instructions that have been executed. And we can add an extra little thing here. We know that volgrind adds about a 10 times overhead in the execution of a program. So if we get back to just running this way, well, it's still basically going back as 0. It's entirely possible the compiler's optimizing away our entire program, but I don't believe it would. So let's switch back to our compiler explorer just to make sure we're not doing something really dumb. Okay. So it kind of appears, let's scroll up to main here. So main tests it, and then it looks like it's saying just multiply the result value of one call to size 10 million times. That is very smart of the compiler, but not really what we're looking for here. So let's maybe try a different compiler and see how smart they are. Now we're getting the same result from Clang. All right, so how do we convince the compiler to actually do some work here? We see how smart its constant folding is. So it calls that, and I have no idea what the LEAQ instruction is doing, but oh, yeah, it looks like it's mostly able to outsmart us still, but I think this still helps us to illustrate our point. Let's see. Well, so now there is actually some time being taken. That's different. And we can see if Valgrind agrees. It does agree. So now we have 351 million instructions that are being executed. All right, very good. So for our second run at this, we need to change this from magic static ref to simply magic static. So we are now calling the magic static function each time instead of returning back our cached reference to the static variable that is part of the C struct. Compile this one. And our timing execution looks like it took about twice as long, but these are definitely within the margin of error. So let's do our more exact test of running against callgrind. There we go. Be interesting to see just how long this takes. All right. So it took 5 times as long, 4 times as long to execute through Valgrind, but that's not a really good indicator of how much extra effort it really was. But we can see that we got 351 million instructions executed with our cached reference version and 801 million instructions executed with our non-cached reference version. So the question of what do we do with this information, I'm not entirely sure. If you watched the previous episode, you would see that I used a technique similar to this in the ChiScript parser refactoring that I did. Is that always a smart thing to do? I don't know. But it's probably something worth considering if you are working with static values that you have to access very many times. So thank you again for joining us for this second episode. And if you have any comments on color schemes or font sizes or anything else that could make these videos better, please let me know. Leave comments on the Patreon site. Thank you.